Professor Stempers, for inviting me to give a talk at this nice workshops. I mean, one day thing. Well, when he asked me to give a talk, I was worried that because most of you are doing algebraic geometry, maybe nobody will understand what's going on here. But he was interested. I mean, he asked me specifically whether I have something related to matroid. And then suddenly, yeah, I have some results very recently. So maybe this is interesting. So that's what I got. So yeah, I mean, you might know this old movie. No, this is not someone. Last month I proved something. So I'm going to show you something that I did last month with some other people. So this was where we made the theorem. You know, do you know where it is? Yeah, Dunkin' Donuts outside, right? So that's where we made the theorem. So that was the last month when I was attending the lectures. All right, so let me start with the problem encoding theory. And this is going to be the all the description of the problem, right? So you're given a vectors, n vectors in a finite field. I mean in a vector space over the finite field F, and you want to find the permutation of them, so that what is 3? Okay, this is I. Okay, so for any I, the span of the left I vectors intersection with the right vectors has dimension less than or equal to k. So you want to find the linear ordering of your vectors, so that wherever you cut, the span of the left-hand side intersection with the span of right-hand side is has the less than k dimension. Okay, so that's what you want to have. So this is a problem. Can you find such a permutation, right? And apparently, this is related to some problem in coding theory. So you want to find some code, right? So you have, I mean, the property of code is that for each alphabet, you want to map it to some word so that the distance between them is satisfy some property, so that whenever you have a small number of errors, you can still decode it. And many of the codes are coming from the linear spaces or vectors. So here you have vectors, but the quality of this vector is measured by some good permutation. So if you have a good permutation, having small dimension for each cut, then you might have a good property that they can use. I don't know exactly, but so they call this minimum. I mean, if you can find some minimum k such that such a permutation exists, then this k is called the trellis state complexity of a linear code, or simply trellis width. And this was a term in coding theory community. And for matroid theorists or graph theorists, they call this a path width. So if you don't know matroid, you have nothing to worry. This is exact description up to some cheating, but so this, I mean, in different community they used to call same thing with different names, and this occurred many times, right? And this has been studied since Robertson and Seymour. They defined the path width of graphs and later generalized it to matroid. And basically, they're matroid representable over some finite field, F representable matroid. You can think of it as just vectors. Okay, so you have n vectors in the vector space over F. And people in the coding theory didn't know this path width until 2007, where Navin heard this result on matroid minors, and then he proved that computing this trellis state complexity is incomplete. This was an open problem for like 10 years, but in fact it was known in the graph theory community, and he just found the connection to prove it. And then in Navin's paper, he made the following remark. So he showed that the trellis state complexity is NP-complete, thus settling a long-standing conjecture. But the situation is different if you fix the parameter W. So now the problem is, so previously you have a K, right? So now you're given some n vectors and number K, and you want to know whether there exists a permutation so that for each cut, the connectivity, the span of left-hand side intersection with the right-hand side has dimension at most K. So previously the K was a part of input. But now, in this problem, K is not a part of input. It's just a fixed constant, all right? And he called it a weak trellis state complexity. So you're given, instead of vector, he said generate matrix, which is same thing. You just look at the column vectors. And you want to find the permutation of the columns so that for each cut, you have a small dimension. Okay? And he mentioned that there is a good reason to believe that this is a polynomial time solvable. So why? Why there is a good reason? And this is because of the progress in matroid theory. So there is a big conjecture, it's called the well-quasi ordering conjecture, saying that for any finite field F, the set of F representable matroid are well quasi-ordered by the minor relation, whatever that means. Which means that if you have infinitely many matroid representative over a fixed finite field, then one is a minor of another. Or you don't have infinite anti-chain with respect to this minor relation. But what is minor? Well, let's say you have a set of vectors, okay? Now you can delete some vector. That's one way to get a minor. Or you can delete some row in a, I'm cheating a little bit, but you can delete some row in a matrix. That's kind of a contraction, but it's not exact, but you can either delete column or row. And the theorem is, this is, the conjecture is that you cannot have infinite list of matroid without having a pair of them where one is a minor of another. Which in fact implies that if you have a property of matroid closed undertaking minors, then there are only finitely many exceptional sets. Right? So you can characterize any matroid property closed undertaking minor in terms of finitely many forbidden minors. And this is occurring in many places. For instance, for planar graph, you can characterize planar graphs by two forbidden minors, K5 and K33. So graph is planar if and only if you don't contain them as a minor. And the important thing is there are only two. And here we have same property. And this conjecture was proved recently by these three people, and Jim Gillan and Bert Herrad, Jeff Whittle. And he's too busy to write a paper, so his email address is now device null. This is from his website. So they are writing this now, but they announced 2 years ago that this conjecture is true. And the corresponding conjecture for graphs were proved by Robertson-Seymour much earlier. So as a corollary, since matroid of paths with most K is closed undertaking minor, you will have a finite list of obstructions so that a matroid has paths with most K if and only if none of the obstruction is a minor of your matroid. All right? So what can you use that? Well, so if you want to know whether your input matroid or whether your input n vectors has trellis with at most K, you can basically test whether or not you contain the exceptional list as a minor. Right? So you might have a million obstructions, okay? So million forbidden minors. Now you have input matroid. Okay, when you do is, well, does it contain this guy? If it contains it, then this is not a matroid of path with at most k, because it contains the forbidden one. So you just test one by one. But since there are only finitely many of them, you can do it in constant time times number of times. I mean, you can do it in polynomial time. So this was the outcome of this. So this is what Navin said. Well, it's believable, but actually it's doable. But this approach has a problem. So the first problem is that there's no algorithm known to generate the list of all forbidden minors. So the theorem just says that, well, there exists some finite list of forbidden minors, but it doesn't say where are they, right? So you don't have any bound on it. Any question?
Wouldn't you also need that the list is polynomial the list itself, like?
Well, there's nothing. List can be huge, but it's constant.
For each k, it's constant.
Yeah, for each k, it's constant.
But I'm saying you need the size of your list to be polynomial.
No. But the algorithm here is that in terms of k, it's going to be huge, like 2 to the 2 to the whatever to the k. So I'm fixing k, so k is constant.
Okay, so because k is fixed.
Yeah, k is constant, so the algorithm will be really slow if k is big. But still, if you're interested in testing whether trellis width is less than 100, then you can use it, right? Because 100 is constant. Yeah, so the first major problem here is that we don't have any algorithm to generate the list. So that's the first problem. And the second problem is that even if you know the algorithm, even if you know the complete list of obstructions, you still don't have the permutation. It just says that, yeah, this is not, this has path width at most k or trellis width at most k just because it doesn't contain any of the forbidden list, any of the forbidden minors. So it doesn't contain bad guys, so it's a good guy. But you cannot say why this is good, right? So we have two problems in the previous approach. And what we are going to do is to present a direct algorithm to find such a permutation. All right? So you're given n vectors in a vector space over the finite field, and we can decide whether there is a permutation, good permutation. And if there's one, then we can also find one. Okay, so that's what we want. Any questions so far? So you can ask whatever questions. I'm happy to answer. There's another notion called branch width. So I should also mention it. So the left-hand side is a path width or trellis width. So you're given n vectors, and when you want to find is a linear ordering, good linear ordering, so that for any cut, the span of vectors on the left-hand side intersection with the span of vectors of the right-hand side has dimension at most k. So that's the and minimum k such that such a permutation exists is the path width, and such a ordering is called the path decomposition. Now we don't want to restrict to a path. We can have a trees. So that's branch width. So the situation is same. You have n vectors, and we output yes if there is a tree, so, where each internal node has degree 3, and the leaves are labeled by the vectors. So that for any edge here, for any edge there, the intersection of the span of the vectors on the left-hand side and the span of vectors on the right-hand side has small dimension. Okay, so this is just variation. Here, you want it to have a small dimension on the left and right. Here, I cut here, then you have 2 vectors on the right and 4 vectors on the left. and I want this dimension to be small for every edge. So if you have such a tree with the labeling on the leaf, then you call it a branch width. Then you say that branch width is at most, less than or equal to k. So the minimum k such that such a tree exists is called the branch width of a matroid. Right? So now you have a path, but now there's a tree. So why do we care about branch width? Well, somehow algorithmically, branch width is easier to handle. And we solve actually both problems at the same time. So the first theorem is to find the path decomposition or linear ordering of the vectors, so that each cut you have a small dimension. And second theorem is you find the tree with the labeling on the leaves, so that for each cut you have a small dimension. Okay, so this is what we prove. And this part is new. And this part, there was an earlier algorithm by Peter Ilani and I using more complicated method, which I will show you later. And this is brief one slide overview of the algorithm. So there are many parameters like path width, branch width, tree width. All of them have the similar framework. So first, what we do is apply some kind of greedy algorithm that will either find some approximate branch decomposition or confirm that you don't have any such tree. So the algorithm either find branch decomposition, but the width, the dimension is big, still bounded by some constant factor, right? So initially, when you wanted to find was a good tree where for each edge you have dimension at most k, but the greedy algorithm cannot guarantee you that you can find it. But you can greedily find something good with a width at most 3 times k. With a factor 3, you can find it efficiently. If this greedy algorithm fails, then we can immediately answer no, because we don't even, that's the point. The algorithm will always succeed if the branch width is at most k. If it finds one, then we use that branch decomposition given by this approximate algorithm to find the forbidden minors in your matroid. And because of this tree structure, we can efficiently test minors. So that was the old idea. And because of the well-quasi ordering theorem by Jim Gillan and others, there are only finitely many minors to test. And you can just repeat this million times. But million is constant with respect to k, right? So that you can do it. But our new method is to use branch decomposition to enumerate all partial solutions. Right? So you have a tree structure, right? So now we start from the bottom. I try to enumerate all partial solutions from the bottom and try to go up one by one. So that's what we are doing here. So let me mention how we do the first step here. How do we do? How do we get an approximate branch decomposition? And this was done by Peter Ilani in a paper published in 2006. So in a cubic time, you can either produce a branch decomposition of width at most 3k. So you can either find a tree where for each edge, the dimension of the intersection of the left-hand side together with the right-hand side is at most 3k. Or it confirms that branch width is bigger than k, which means that you can immediately stop. There's no branch decomposition of width less than or equal to k. There's no path decomposition. So that's one ingredient in his paper. And there's another ingredient in his paper, which he also answered the second step. For any fixed matroid n, you can test whether or not your input matroid contains n as a minor. So you fix n. Then whenever you are given new matroid m, you can decide whether or not it contains an n as a minor if this input matroid has small branch width and it comes with a decomposition tree. Right? So you give the decomposition tree. Now you can decide by using this tree, you can decide whether or not you contain something as a minor. And because of well-caused ordering theorem, you only have finitely many forbidden minors, so we were able to decide in polynomial time. And there were different stories for branch width and path width. So for branch width, there was a theorem by these 4 people saying that the forbidden minors cannot be too big. There's an upper bound. Right? So forbidden minors for branch width at most k can have at most 6 to k elements. Which means that if you're interested in just theoretical algorithm, then you can generate them all. Well, in theory, right? K is constant. So in a constant time, you can search all matroid or all possible vectors of, all possible 6 to the k vectors, enumerate them all, try all possible trees, test whether or not they have a branch width bigger than k or not, right? So you can generate all possible forbidden minors, and that will give you an algorithm, right? So we know the algorithm. Okay, we know how to generate all forbidden minors for branch width. Once we know that, then we can use it to you can use it to decide whether or not a matroid has branch width at most k. And the situation is different for path width because there's no such bound known. So we have a lower bound saying that the number of forbidden minor grows exponentially. I think it's double exponential. But we don't have an upper bound. The only upper bound is the consequence of well-caused ordering theorem, which says that there are only finitely many. So there should exist an upper bound, but nobody knows. But because of this existence result, we know the existence of polynomial time algorithm, but we don't know the algorithm. So there's a certain difference between the existence and knowing the algorithm, right? People know how, we know there exists an algorithm, but nobody know how to construct one. Until now, right? So we have a theorem now. Yeah, so that's what I said here, right? So the branch width, we can do it in constant time. We can generate all forbidden minors, but path width we cannot do it. So that was the first difficulty. The second difficulty was to convert a decision algorithm to a search algorithm, because previous approach just says that, well, if branch width is big, then you have one of the forbidden minor inside your matroid. But if branch width is small, that just means that you don't contain any of the forbidden minor, which doesn't give you tree or which doesn't give you permutation. But for branch width, we use some kind of complicated techniques, like extending the underlying field, attaching some gadget and some properties in GraphMiner papers. We were able to come up with some algorithm to find the tree from a decision algorithm. But for path width, nobody knew. Right, so that was the old approach. Do you have any questions?
Can I ask just a very basic question?
Sure, yeah.
Just to get a bit of more of an intuition of
All right.
a good ordering. So, for instance, the graphic case, suppose I have a graphic matrix.
Yep.
I want to label the edges. Can you just say a sentence or two, how should I think about a good matrix?
Right, so you want to have a permutation of edges so that whenever you look at like first 10 edges versus remaining, the number of vertices, meaning both sides, is small. Right? So you take the first I edges and remaining edges, the number of vertices which is in common to both sides is small, and this property is kept. So basically the graph will look like the thickening of path-like graph. So you have some box here, you have a small boundary, you have another box, small boundary. So it's like a path. And if you have a small branch width, then
Build up the graph in a way that always has the boundary is small.
yeah, so the boundary is always kept to be small.
Thank you, that's useful.
Oh yeah, all right. Any other questions? Right. So I'm going to show you the algorithm, the new algorithm, which I haven't given any talk before. So yeah, this is a challenging project. Actually, my co-author Eunjung met Dimitrios Tilikos, who did a similar work for graph theory. And she said that we proved this algorithm. And then Dimitrios said that writing that algorithm cannot be done by human. It needs some kind of computer or something. I will explain what's going on. Anyway, so the main tool is the dynamic programming. So what is the dynamic programming? Well, I just Googled dynamic programming. Then there was a Stack Overflow page. So I will show you two pictures. If you want to compute Fibonacci numbers, just from the definition, right? So the Fibonacci number, you just add the first two entries. If you just call it recursively, right? If you naively write a program like this, right? Then the running time is going to be exponential. This is trivial, right? You call, well, let's compute n-1. Let's compute n-2 and add them together. You have a tree, binary tree of depths n. So it will take exponential time. But if you memorize partial solution, then it only takes a linear time. The point is that you only need to memorize previous two terms. Then you can compute the next one, right? So that will speed up the algorithm a lot. And this is what we are going to use here. So what kind of things do we memorize? And we need to have some kind of description of matroid or vectors having bounded branch width. So from now on, if you don't know what matroid is, you can think of it as a multi-set of vectors. Right? So you have a multi-set of vectors. That's a matroid. And Hillern's algorithm will already give you some tree. Right? So you already have a tree with 3 times k. Let me call it w. And you have a tree. Now, what you want to do is to compute some partial solution from the bottom. Now, what I do is now define something called the boundaried matroid. So here you have a picture. So I have some matroid M, which means that inside here I have vectors, v1 up to vn, and some boundary B, which is a subspace. And the point is that later on I will build my new matroid or bigger matroid from smaller matroid by gluing along this boundary. Okay, so inside matroid I will not do anything, but the goal is the following. So if matroid has branch width less than or equal to w, then I can build it from trivial matroid by some of the operations. So I have some building like blocks. Yeah, I have several blocks. Now I want to glue them together in a certain way so that my new matroid is obtained from these building blocks. And this gluing operation, I have 3 operations here. So what the trivial operation is expand. So what it is to do, what it does is to extend the boundary B to a bigger space. So you have n vectors here, you have some boundary space. Now I want to expand this boundary space to a bigger subspace. But the problem is that I don't want it to be, I don't want this new part to interfere with any of the existing vectors. So you can think of it as extending B to a direction where it's orthogonal to any of the previous vectors. So I'm trying to extend my boundary to some direction where it doesn't interfere, it doesn't have, it's going to be orthogonal to any of the existing vectors. So that's an expanding operation, which will increase the boundary. And there's a shrinking operation, which is simple. You take a subspace of the boundary, and you replace it. Now you declare this B prime as your boundary. So these are just simple operations. You keep the same set of vectors, but you declare that this side is boundary. Later on, I will glue something on the boundary. But even if I glue something on the boundary, it doesn't interfere with existing vectors if they are not on the boundary. Yeah?
So what is the boundary matroid? Is it some matroid?
A boundary is a subspace. It's not a matroid, it's a subspace.
Flat.
No, it doesn't matter. I mean, whole thing is a vector space, right? So everything is embedded in the vector space, right? M is a collection of vectors, n vectors, and B is a subspace.
So that those vectors is a spanning set of that vector space.
No, M might span it, or M might not span it. If you expand it, then the n vectors doesn't span B prime. But this is independent, right? M and B are independent to each other. Maybe M may span B, but maybe it doesn't span B. It doesn't matter. So I basically, let's think of our, three-dimensional space. I have maybe 10 vectors. And I might have some subspace of dimension 2 somewhere. And that's it.
Yeah, so now you're talking about vector space in a matrix.
Yeah.
So we have what's the relation?
Right, so that's what comes next, join of two. So the important thing is when I join two boundary to matroid, I'm going to use this boundary. So suppose I have two boundary matroid with the same boundary space, B and B. Now what you do is, first of all, I make sure that nobody here interfere with nobody there. So everything is orthogonal to that. And then I glue them together, sharing the same boundary space. So that's going to be the join operation. So for instance, you have, let's imagine that you have vectors spanning on this plane, okay, where the boundary is this line, right? Now I have another vectors on this plane with the boundary on the same line. Then I can glue them together, sharing the same line. Okay? Does that make sense? Right? So that's what I want. Right? So I want to overlap these two boundaries matroid along with this same boundary. And basically, these three operations are enough. If you have a branch width and most W, then you can construct your matroid from trivial matroid by using these three operations while keeping the dimension of B to be at most constant, twice W. So when you expand and shrink, this dimension might change, right? But the dimension is bounded by twice W, which is still constant. So that's basic, that's a description of the ways to build your matroid. And then we need to have a dynamic programming. So the idea is that now imagine that you know how to make your matroid from trivial one by expanding and gluing, joining and shrinking, etc. You repeat this process until you get your matroid, right? So yeah?
Are you gluing your matroid or your vector spaces or your matrices?
Okay, so we are gluing vectors, right? So this works for representative matroid. So yeah. So in some cases you have to rotate it and glue, right?
You are gluing vector spaces?
Yeah, so everything is for represented matroid. So we are talking about linear algebra thing. Okay. All right, so we have a kind of tree structure that describe how we join these trivial ones together with others to make our matroid. And then for each intermediate step, we want to keep certain partial solutions. Right? So what kind of information do I need to memorize? Right? So for Fibonacci numbers, you only need to memorize previous two terms. But now, what should I memorize? Right? Imagine that I have some bounded matroid with the vectors, n vectors inside it. Later on, I might need to join it with some other matroid here, right? With maybe 10 vectors. Now I need to have a permutation later, right? Which interlace these two permutations. So what kind of information should I think of, right? So let's say V1 of the Vn is a potential permutation, which might be extended to a real permutation later. This is subsequence of linear ordering that we were looking for. So first of all, for each cut, I will denote xi as the space spanned by its left-hand side, and yi to be the space spanned by the right-hand side. And then we have three kinds of information. So first of all, if you look at the x1 intersection with b, right? So I'm looking at the space inside b, how these guys behave. But x1, x2, x3 were increasing sequence of subspaces. So if I take intersection with b, this is still increasing sequence of subspaces. So you have one increasing chain of subspaces of b. And if I look at y, then that gives me a decreasing chain of subspaces in b. So these are like what's happening on the boundary, which might interfere with outside world, okay? And inside of M, not on B, you're not going to interfere with outside world. We might forget some unnecessary information. So we want to have some essence of this thing. So say it's called internal connectivity, which is like, what is the dimension of x1 intersection with y1? We want this number to be less than or equal to k. But these numbers, so we have a sequences, right? N numbers. So you might think, well, how about this, right? So you keep this information, this chain, and these numbers, yeah, sequence of numbers. So for each bounded matroid occurring in this tree, you enumerate all possible triples of a chain and sequences. And then maybe you can enumerate how to glue these, how to merge these partial solutions. And you go up. But the problem is that there are simply too many. But the good news is that for these two chains, because B has a small dimension, number of distinct subspace that appear in this chain is bounded. Right? B has dimension at most twice W. So you cannot have too many distinct subspaces. So that's one key idea. But still, we have this problem. We have sequences which might be arbitrary, and this have length n. So how can he reduce or how can he compress this sequence so that the answer doesn't change, right? So I don't want to have unnecessary information to be memorized. I want to remember only the minimum amount of information. That will ensure faster algorithm. And there is a nice idea by Hans Bodlander, who used similar idea to have an algorithm for graphs. And he called it a typical sequence. So the basic thing, the thing is that imagine that you get sequence like 1, 3, 7, 4, 5, 6, 3, 2. That's maybe let's think of it as a dimension, right? So you have dimension 1, 3, 7, 4, 5, 6, 3, 2. When you join it with some other matroid, some other boundaried matroid, you will interlace these two sequences. Then probably it doesn't matter where you cut. You're adding a vector out from the outside world and insert it in between here. But probably that will increase this number or that number. But it doesn't really matter. For instance, number 3 really doesn't matter, because if you happen to increase 3, you might increase 7 or 1. And you want to keep these sequences to have numbers at most k. So the danger is this bigger number, 7. You don't really worry about 3. It's squeezed between two numbers, minimal one and maximal ones. So basically you can forget about this number 3 and get a smaller, shorter sequence. So whenever you have a sequence like this, given by the previous dimension sequences, let's forget about this 3 because it's between 1 and 7. And similarly, whenever you have like 7 and 2, maybe my reduction was wrong. I have to reduce more. 7 and 2, so 4, 6 are between 7 and 2, so I have to remove 4, 6 as well. So I can get the key essence of the sequences, right? So if you have a dimension sequences, I can just remove unnecessary information to have an essence of the sequence, and which will not change the solution. So this is called the reducing operation for a sequence. If you have a sequence, whenever something is between these two numbers, you can remove something in the middle. And a sequence is typical if no further reducing is possible. You cannot reduce anymore. And then the Bodlander and Tom Clark had a lemma saying that number of distinct typical sequences having the numbers from 0 to k is small. It's bounded by a function of k. So previously we had a sequence of length n. So it grows with n, but now it doesn't grow with n. It's only k. So I don't have to worry about too many partial solutions to remember. I will only remember partial solutions of size small. That's my goal. So what kind of partial solution do I remember? Right, we used to have an increasing chain of subspaces and decreasing chain of subspaces. But this chain has length n, but you only have small number of distinct subspaces. So I record where it happens, right? So let's say this was dimension 1. Now there was a jump. I have dimension 2. There was a jump. I have dimension 3, etc. And this was decreasing sequence, decreasing chain of subspaces. So here you have dimension 0 and 1, 2, 3, 4, 5, right? So now I overlap these two chain. They will induce lots of intervals. But the number of such interval is at most 4 times w plus some constant. And for each interval, I look at the dimension sequences. right? So you remember the internal connectivity like this, dimension of x1 intersection y1, x intersection y2. And you look at these numbers for each interval and reduce them. But number of typical sequences here is at most 2 to the 2k. And for each interval, I have 2 to the 2k possible sequences to remember. So that means that, well, I only have a bounded amount of information, right? So I will remember these markers for this chain, right? So what kind of subspaces that occur in the chain, what subspaces that occur in the chain. I also remember the order. And for each interval, I remember a typical sequence, which is also bounded information. So the number of distinct triples, triple of chain, and these sequence of typical sequences is bounded by a function depending only on the size of field and k, but it doesn't depend on n. So that's the information that we keep in the iteration. Now, the remaining part, well, I'm going to be very brief. So we will do this one of three operations. Either we expanding a boundary, or shrinking the boundary, or joining two boundaries matroid. For each of these operations, I have a way to update the partial solutions. Right? So for instance, imagine that you shrink the subspace, shrink B to a subspace, B prime. Well, you look at and assuming, you can assume that you already have a list of partial solutions here. But then you can shrink for each chain, for each partial solution. You can take intersection with the B prime and reduce the typical sequences further. That way you can shrink it. And expanding is similar because you're not doing much. I mean, expanding, you can just keep the same partial solutions. Joining is more non-trivial, but still you can enumerate all possible ways to make a chain, two chains here, and then enumerate all possible ways to construct that chain by summing two chains from here and there, and then you have a partial solution there, partial solution there. I mean, the amount of running time here is still constant. It doesn't depend on the size of matroid. So that's why I'm trying. There's lots of things to write. But after this whole process, then you have a matrix. If the list of partial solution is non-empty at the last moment, then the answer is yes, meaning that there is some good permutation. If the list of partial solution is empty, that means no, there's no way to find the permutation. So that's how we can decide whether or not there's a good permutation. And if you reverse, if you backtrack every process, you can also construct the permutation as well in the same running time. So this is the whole picture for path width. And for branch width, a similar idea works, but instead of a path with the intervals, now it's a tree, right? We have a tree here. So what kind of information do we keep? Well, now it's more complicated, right? For each edge, I need to remember these chains of subsequences with intervals, right? For each interval, you have typical sequences. For every edge, we do that. So that's a partial solution. But then I have to reduce. I think I have to reduce more, probably. Yeah, I will. So this is summary. So we have a direct algorithm that can search the path decomposition of width and most k, or good permutation, where for every cut you have a small dimension on the intersection. And we can also do a similar thing for branch width. And has consequences to coding theory, something called trellis state complexity. And has consequences, I didn't mention this, but there's a corollary to graph theory. And because something called rank width can be computed from the branch width of matroid. Okay, so that's it. Thank you for your attention. Yeah, thank you.